25 through. All right, I think this is the new book. Is your 25 a graph? Carter, you fixing to get on my nerves. That looks like that. Oops. -1, 4, 2, 2, 5, 5.
You're like pages were wrong.
Yeah. Because I wasn't finished doing my homework because the numbers were right.
Well, that's what I just asked you. Did I have the right book? What's on your page 94?
It was 93.
Well, I want to make sure that I have the new one.
You have the old Tyler Road. Yeah, it's page 93.
Okay. Let me not get confused. Let me put this up. I did the same with Kelly. All right. The problem is still this, right? Yes.
Yeah.
State whether each point labeled identifies a local min, max, or neither. Identify the intervals on which the function is decreasing and increasing. I'm going to do this and call this a continuous function that goes on forever, just for the sake of example here. All right, so the first one, -1, 4, what is it? Max, min. That's right. How about 2, 2? Same thing. 2, 2? I'm going to go with local or relative here. Why? This is going down. For one, on my picture, but even on yours, if you look, there is, let me show you. Local and relative mean the same thing. I'm fixing to show you. Local and relative mean the same thing. So if you look at this one, that is a minimum, but if you look, the graph goes down lower than that at some point. Does that make sense? All right, so we got relative max, relative min, absolute max. Why is that one absolute? It's the very top. It never goes higher than that, right? Does everybody see that? The tippy top. The absolute highest. All right, that's only half of it, though, to do that. So now let's talk about the increasing, decreasing intervals. From negative infinity, if my graph goes down forever, from negative infinity until I get to what? -1, is that increasing or decreasing? Increasing. And then from 1 to 2, that's decreasing. From 2 to 5, increasing. So I'm going to join that with the increasing one. And then from 5 to infinity, decreasing. I would be happy to. Sorry. What else? Is that good? Y'all good on that one? Okay, what else? 35? Why does it keep doing?
Yeah, I didn't get 35.
What's it doing? They just want me to get up a minute. 35. Determine whether the function is bounded above, bounded below, or bounded on its domain. So I have y equals 32. What kind of line is y equals 32? Okay, all lines are straight, but what kind of straight line is it? Okay, so what's it look like? There you go. Everybody's doing that. What's that called? Horizontal line. Yeah. Is that bounded above, bounded below, or bounded? It's just bounded. It's just bounded. So if it doesn't go above a certain point ever, it's bounded above. If it doesn't go below a certain point ever, it's bounded below. If it's both, it's just bounded on its domain. Not all of them, because
That is true.
what if I have that? That's bounded below. Well, it depends. If it does this, that's unbounded. Because, yeah, it doesn't have it top out and it doesn't bottom out.
So what is bounded below me?
What about what? This? Something like that?
Yeah, that's bounded below.
Bounded below.
And what's bounded above?
That wouldn't be both.
Oh,
I get it. I get it.
Y'all got the boundedness?
Yes.
Sure. So this would be bounded above. This one would be bounded below. This one is not bounded. Not bounded. That's not. This is not technical terms here, y'all. And the straight line is just bounded. Yeah. This one's bounded below. And this one is just bounded on its domain because it doesn't go above or below a certain point. Which one did you say, Liv? 40. X minus x cubed?
Yeah.
Is that right? Yeah. Is that 40? Okay. All right, so 40 is y equals x minus x cubed. Let me see what that looks like. That looks something like this.
Unbounded.
Unbounded. Unbounded.
Precisely.
Good job, Carter. Be nice about it, though, but get it right. What else from your homework? Did we stop with, what did y'all stop with? So a removable discontinuity is a hole. If this was my graph and that was an open circle, that would be removable. When just one point is removed from the graph, that's removable. Non-removable are things like jump discontinuities, infinite discontinuities. Those are non-removable. What else? Did y'all have any of those? Oh yeah, in the beginning. What type of discontinuity? Did it again? What the heck is going on?
That was good.
Are you doing that, Carter? Are you doing something? I don't know. Because I've heard him do stuff like that to Chick before.
Let me use my brain. No, I can't.
Get out because my screen keeps cutting off. 41.
I was like,
Carter probably did it.
I was like, this might be the dumbest thing I've ever encountered.
But then that's probably why you got kicked out, because you're arguing. Use a grapher to find all local maximum, minima, and places of X where they occur. Give it rounded. So, here we go. Y equals 4 minus X plus X squared. Oh. Second trace. Good job. Does it have a minimum or a maximum? A minimum. Left bound, enter. Right bound, enter. Enter again. The X value there, 0.5. Look, that's it. That's it. Anything else from your homework? Oh. How do I get what? Oh, second trace, and then I chose minimum. And it doesn't. That's right. I generally, yeah. Look at you. Just ask Carter. He'll teach. Put the spider close to where it actually is, and then do what it tells you. So click about 3 left, hit enter, go back to that place you're looking for, and then right 3 times, enter. Yep. Just approximately where it is, and then you go left. 3 times usually clears you that you know you're past the actual point you're looking for. That's why I say 3. What else? Yeah. The missing point. Oh, is that like you couldn't see all the graph? Yes. Hit window. This tells you what your X goes out to. So this is saying that whenever I'm looking at the graph, it goes from -10 to 10. If I wanted to see more this way, when I hit window, I could change it to maybe -20 to 20. So now instead of see, now there's 20 dash marks each way. Same with the Y. If I want to see more up and down, maybe I don't want to see that bottom, so I change it from 0 up to 20. So now, and if you ever zoom 6, you'll be back to 10 by 10. Other questions? We're holding off on the quiz until probably tomorrow when we finish this section finally. The rest of the analysis. What we've been doing, boundedness, symmetry, maxes, mins, and then we got some more to do. Did we do even odd Friday? We stopped with asymptotes, that's right. Before we start, let me just introduce you to limits. So, limits are especially helpful whenever we get really close to something, but we don't actually equal it, or if we're getting really close to a big number, or the best way to define limits. I think we should just do limits. Why do we have? Okay. Here's what we write. This is read as the limit as x approaches, and this can be a number, this can be infinity, this could be anything. Let's say the limit as x approaches 5, and then I'll have some function over here. So maybe This is an easy one because the limit as x approaches 2x plus 3. The limit as x approaches 5 of 2x plus 3. Okay? Just means the closer I get to 5, what value does this take on? Well, this one actually has a value at 5, right? You can just plug that in and know, well, that's 13, right? But what happens one, two. I'm going to call this f of x. What do you think is the limit as x approaches 2 here of f of x? So look at that graph, and as x gets closer and closer to 2, what is happening to my graph? How do I say that? Okay, how do I say that conceptually? It's going down forever really fast. You're right, infinity, negative infinity. Okay? Did I not? Ugh. What if I asked you, now this is, let's call this g of x. What if I said, what's the limit as x approaches infinity of g of x? What would you think that might be? What's the graph doing? As x approaches infinity, it goes to 2. You're exactly right. It's getting closer and closer to 2. This is how we're using limits, and that's really all I need you to know right now. I'm not going to delve too what? We did. This is a little bit more of a calculus-y way to look at asymptotes. Okay. These are called, well, I just said it, asymptotes. So tell me again what an asymptote is exactly. You're exactly right. An asymptote is this invisible boundary. It's not actually a part of the graph, so I say invisible, but it bounds the graph just the same. So your graph is not going to cross that asymptote. Now, just because an asymptote is bounding, and this is where we start getting past the Algebra 2 stuff and into a little bit of the pre-cal stuff, asymptotes can bound the right side of the graph, but not the left side of the graph. They could be present. In other words, this could exist just to bound this piece, and there could be something else over here that's coming doing this. Okay? It doesn't necessarily bound in the same place all the way across. It's invisible. It can do that. 9 times out of 10, it will bound everything there. All right, do we all know what asymptotes are? Let me formally define an asymptote for you then. A horizontal asymptote, which I will call aha. Yeah, but nobody else wants.
Oh yeah. Oh yeah.
If you can take the limit as x approaches infinity, or the limit as x approaches negative infinity. So either way you look, bless you, to the left or to the right, as far as you look, If it approaches a constant, okay, just a number, just a value, then y equals b. Come on. Is an asymptote. If you keep looking, and as your graph goes as far to the left or the right as you can go, if it's getting closer to a number, some constant, then that constant is your asymptote, your horizontal asymptote. Did we do this?
Yeah, we did. No, we didn't do it.
Well, I'm going to show you how to find them now too. But this is the formal definition. And then if you want a vertical asymptote, if you take the limit as you approach a number, some number, any number, and you get infinity, positive or negative infinity, this is a vertical asymptote. It makes sense. We just did it whenever I was showing you what a limit was. This is a terrible seat right here, I feel like. I feel like you two have the worst seats. Do y'all not feel like that? Do you feel like you have to turn your neck to see? You're good? Okay. Okay, clearly you're chilling, so. All right, so let's talk about how we find these two types of asymptotes. Poor Carter. You got a good seat. How to find asymptotes. Algebraically. Which one do you want to do first, horizontal or vertical? Okay, thank you. I feel like we might have touched on this last year. Maybe we didn't. We're supposed to get to it in Algebra 2. If we didn't, I apologize. We'll get to it now. For this, we're looking for rational functions are the ones that are giving us right now our horizontal asymptote. What's a rational function? What do you think of whenever I say rational?
A whole number.
Rational. Rational numbers can be written as, it starts with an F, but it's not a bad word. Fraction. Who was it? Was it my sister? It was probably my sister. All right, rational functions, we're talking in terms of fractions, okay? When I tell you what I'm fixing to tell you, I am referencing their degree. What is the degree of a polynomial? Good job, Noah. The biggest exponent. But yes, the biggest exponent. Good job. All right. If I am top heavy, in other words, by top heavy, what I mean is the degree of the top is bigger than the degree of the bottom. Do you understand what I'm saying? For example, what's the degree of the top? What's the degree of the bottom? 2. If I am top heavy, I have no horizontal asymptote. Okay, there's 3 scenarios. scenario 2. This is very important, by the way. You might want to write this down, star it or highlight it or something, because you'll go back and look at this a lot. How to find horizontal asymptotes, and then how to find vertical asymptotes. All right. Why don't you go sit on the other side of me a seat? Be able to see a little better. Very nice of you to offer. Bottom heavy. What do you think that means? Bigger on the bottom. The degree is bigger on the bottom than on the top. So if we just took this one, what? Stop. Bottom heavy? If that occurs, then your horizontal asymptote is y equals 0. What other possible scenario could I have? They're the same. If the degrees are the same. For example, just kidding. Degrees are the same, yes? If that what? Then your horizontal asymptote is y equals the leading coefficient of the top divided by the leading coefficient of the bottom. So in the case of this one, what would my horizontal asymptote be? Just the leading coefficient, 3 seconds. 3 over 2 is my horizontal asymptote in this case. Okay, so I'm looking at the equation and I'm doing some analysis and I'm going, okay, is it top heavy, bottom heavy, or the same? And that's going to determine where my horizontal asymptote falls. Does that make sense? Let's look at an example. See if it really does. Y'all got that? Can I move? Does this one have a horizontal asymptote? If so, where? It's bottom heavy, which tells me what? Y equals 0. See how we're literally just using that? What are you doing, Carter? What say you, Carter? Where's the horizontal asymptote? There's none. Why is there none? It's top heavy. Does everybody see what we're doing here? Top heavy, none. Bottom heavy, 0. Same is the leading coefficients at the top and the bottom. Where's the horizontal asymptote? It doesn't have one. Top heavy, bottom heavy, same. You know that part that I said make sure you write down, start, or highlight it in your notes or something? You wrote all this down? You got top heavy, bottom heavy, same? So look at that one. Was it top heavy, bottom heavy, or same? Degree of the top and degree of the bottom, 4. So is it top heavy, bottom heavy, or same? Top heavy. What's your sheet say for top heavy? Where's your horizontal asymptote? This is why we got away from guided notes, is because you've got to learn to. All right, what's it say? Look, what's it say, Carter? You need another break? Yeah, y'all need another break before we do verticals. I'm seeing everybody do this. Is this hard or is this dull? Do I sound like Ben Stein up here? All right, so you have to be able to identify both vertical and horizontal asymptotes. We're still looking at the same rational functions. So I'm looking at fractions. But here's what I want to look for. Look at.
There's only one boy in the top boy. Yeah, and then there's like four. You like 19? Miss McGee.
Stop! Don't blame me. All right, look at the denominator. We want to know, where does the denominator equal 0? These are going to produce vertical asymptotes with one exception. Are you ready to know what that exception is? I'm so excited to hear what that exception is. When factors cancel out, it doesn't create an asymptote, it creates a hole. You know how y'all were talking about, where does that come from? Why is there a hole in the graph? You know what I'm talking about? So y'all were like, look, does that really happen when you have something like this and there's just a hole there? That removable discontinuity. This is why we call it removable, because you can remove the factor from the equation. Okay, so let me show you what that looks like, and we can determine about some vertical asymptotes. Y'all got that? All right, let's start with that same equation we looked at a minute ago. Here's where you're going to have to use your algebra 2. We already determined horizontal asymptotes here, right? What does that mean? Horizontal asymptotes, what and where? Carter, horizontal asymptotes, what are they? Why is it 0? Bottom heavy. We already did this one, right? Now let's look at vertical asymptotes. As I determine if it has vertical asymptotes and where they are, but this one's bottom heavy. I want to see, where does this equal 0? Well, this looks like an algebra 2 problem, doesn't it? Factor and solve, quadratic formula, graph and find the intercepts, complete the square. Any of those methods will, huh? What? So for vertical asymptotes, we only want to look where the denominator is 0. Because we can't divide by 0, right? We can't have 0 in the bottom, it makes us undefined. So I'm looking at, where does the bottom, horizontal asymptotes come from top heavy, bottom heavy, same. Right? So this was bottom heavy. Are y'all tracking with me? So for the vertical asymptote, I want to know, where does the bottom equal 0? Well, when does x squared minus 2x minus, or x squared minus x minus 2 equal 0? When x is 0? Oh, wait. Yeah, that would be negative 2. shortcut this one because there's no leading coefficient. What multiplies to -2 but adds to -1? That's right. So what are the solutions here? 2 and -1. Those should be vertical asymptotes on my graph, right? So if I graph this, I should have a horizontal asymptote at 0 and 2 vertical asymptotes at -1 and 2. Now, nothing canceled out here, right? I could rewrite this as x over x minus 2, x plus 1. Nothing canceled. And I'm going to show you one in just a minute that cancels. And if it, let's say it was like this, that would mean there's a hole at 2. Well, let's see what it looks like on the graph. Let's look at it. I'm glad you asked. Remember what I have and what it should look like, and let's make sure that that's what it looks like. Come on. What in the world? I keep clicking it. Oh, this is ridiculous. There we go. Carter, stop messing with the computer. Y equals, and I'm going to input this. What do I have? X over X over X squared minus 2X. Nope, X squared minus X minus 2. I should have one horizontal asymptote at 0. Remember, my calculator's a little funky. Let me zoom in a little bit for you. Let me go -5 to 5. Now, do you see it? There's my 2 vertical asymptotes. And I also have a horizontal asymptote here that's bounding the graph this way. Remember that definition of an asymptote? A horizontal asymptote, as I go to the left or the right, does it get closer and closer to a number? Yep, so I have a horizontal asymptote. And is there ever a time when I get closer to a number that I approach positive or negative infinity? Yes, that's my vertical asymptote. See how it hugs it down really fast or up really fast? That's a vertical asymptote. So good? So all you're going to do, because you're asked to find the asymptotes, you have a horizontal asymptote at y equals 0, and you have 2 vertical asymptotes at x equals 2 and x equals -1. Let's do one more. We won't do it graphically, we'll just do it algebraically. And then we need to review in behavior real quick and I'll be done. Ooh, this is number 62 from your homework. Find all horizontal, vertical, and vertical asymptotes. What shall I do first? It's bottom heavy. Bottom heavy tells me about my horizontal asymptotes. If it's bottom heavy, what does that tell me? Y equals 0. Vertical asymptotes.
We're gonna have to work it out.
We're going to have to work it out. I'm just going to do the difference of 2 squares here, and I'm going to show you why in just a second. Are those both vertical asymptotes? Sure? What cancels? If I have 2x minus 4 over x minus 2, x plus 2, This is this, yes? Oh, what do you notice now? That means that this is a vertical asymptote, but what is this? What did we say that means? It's a hole. It's a hole. This one only has one vertical asymptote. Okay, so this is what, remember we said a hole is removable discontinuity? We call it removable because, look, I can remove that factor if I factor it. And essentially this is 2 over x plus 2. So this creates the vertical asymptote. But because this was in there originally, I have to leave it out. So it still creates a hole. So I can remove the factor, but I have to put a hole there. So it's called a removable discontinuity. So this is one that has a vertical asymptote and a hole, and a horizontal asymptote. The hole is at 2. So if you graph it, it'll look like it goes through 2. But remember, if you go in that table, you'll see that it's not defined at 2. Because it canceled out. No, it'll stay in the problem. It's still there. But yeah. It's where the denominator equals 0, but but it doesn't cancel out. Do y'all need me to go over in behavior, or do you remember it? Well, you're not really going to have in behavior quite like that. I think you're good. It's not going to be... I'd have to get into in behavior of rationals, and I don't want to do that with you right yet. I don't want to do that right now. Okay, so what I want you to do for homework, which you have... Oh, y'all have a long time.
Homework.
I'll give it to you and let you get it done. Probably have a quiz tomorrow after we go over. And it's no, I don't want to. We'll just do a quiz. It won't be a test. That's it.